All right. Yeah, today we're going to be talking about Rust, which is undoubtedly my favorite programming language. And I guess let's start off with how I actually got into Rust. I don't know if that's an entirely accurate statement, but here's the story anyway. When I finished, right when I finished undergrad, and I studied math at Berkeley. After that, I decided to do Hack Reactor, uh, which is pretty much like a forerunner boot camp, a boot camp that was kind of like served as a forerunner for Lambda School, and that one was in San Francisco and in person, and of course you had to pay up front. But anyways, so I did that. That was where I met Ben, incidentally, but also that was that was where I first got exposed to Rust. And back then, Rust was this was maybe like a year before they were even 1.0. So like the language was like really new at that point. But even then, it had a lot of people who were really enthusiastic about it. And one of those people was basically one of the, I guess they were the equivalent of PMs at Hack Reactor. He was this like at the time this 18-year-old kid who decided to not go to college and just pursue programming. And I guess he decided he didn't need college in order to do that. And he was super freaking smart. And I don't know, it's just kind of hard to describe his vibe. But anyways, uh, he was all the time programming things in Rust, and he like contributed a bunch of like open source code to the language. And I think he definitely contributed to uh, Rust's kind of like major HTTP library. He contributed to one like the um, major frameworks for writing server backends in Rust. So he was like really deep in the weeds, and oftentimes I kind of would just like look over his shoulder to see what he was working on, and that's kind of how I got introduced to it. Uh, and what's turned out was really funny is so of course a Hack Reactor also had like capstone projects, right? Very same idea. You had a month to uh, build a project with your group. At least, well, what's nice with those groups at Hack Reactors that you actually met in person. So the dynamic was a little different, but my group actually it wasn't just me who was kind of influenced by him. He influenced a lot of people in our cohort, of course, and actually everyone in our group agreed that we would actually learn Rust for our project. And I think we ended up writing a really simple HTML parser. So, and again, Hack Reactor was all in JS. So in our case, for the people in my group and we were like, we want to take this capstone project as an opportunity to broaden our horizons. We want to learn a language that's very different from JavaScript, and that's what we did. I feel like in retrospect, the project we came up with was a bit underwhelming, which I guess isn't too surprising given that we had to spend like at least half of our project time just figuring out the language and how to work in it effectively. But that was a fun experience. But what was also interesting is that I certainly don't feel like after that project that I really knew what I was doing with the language. So certainly at that point, I felt like I hadn't really learned Rust at all. And plus, since this was pre 1.0, there was, I think the syntax has changed quite a bit since then. Um, and so, like as I mentioned yesterday, or I don't know, I forget if I mentioned this to you guys. Like I've been learning Rust on and off for like basically since then, and it's been like about 4 years. Yeah, about 4 years since then. So like even though I say the language is my favorite, I also feel like by far it's the one I really feel the least comfortable in. And I don't think it's I don't really know what it is about the language. It's just I just kind of feel like this the skill ceiling for it is really really high. Um, Plus also the fact that I hadn't again I feel like if Rust is your first low level language that you're ever like exposed to, it's going to be a little rough if you're trying to learn it because again I think for learning things like C and basic memory management and stuff like that, or for learning things like pointers and basic memory management and things like that, I think that's where C really shines because C doesn't present any sort of veneer over those concepts. Um, so I certainly think kind of to make your Rust learning experience kind of as smooth as possible, you probably want some experience with another low level language first, so that you don't even really you don't have like that cognitive overload of just being like, oh, what's a pointer again? What's a reference? What's an address in memory, et cetera, et cetera. It really helps to kind of go into it already knowing all that stuff. So certainly like after I'd learned and gotten comfortable with C, that certainly helped me to then go back to Rust and revisit it and be like, oh, so now certain parts of it are making more sense to me than it used to. And that's really been the process up to this day. And again, to this day, I still don't feel like I have a particularly strong grasp of the language. But I do find it really fascinating, and I really like working in it. And honestly, I feel like part of it is kind of irrational because at the end of the day, like programming languages are just tools, right? Like they're just a vehicle for you to write programs and get stuff done in it. But I almost feel like it's kind of the inverse with me and Rust, in that I just kind of want to find excuses to write more Rust code. It doesn't really matter what I'm doing with it. Right? Like I don't have like an end goal project that I want to build with it. I kind of just want to write more of it. It's really weird, and I don't really feel like I can explain it adequately. I mean, my relationship with this language. Nice. Never talk about Lisp at all, though. Anyways, okay. So with that being said, let's get into the actual presentation. So yesterday, when you guys said it'd be cool to get a presentation on Rust, I had to do quite a bit of thinking, and because the language is really big and there's many different aspects to it, I kind of had to think about, okay, let's just think about one concept. What's like kind of the most what's really like the linchpin concept or feature that Rust presents that really sets it apart from other languages. And so that's basically what we're going to be talking about today. That particular feature is called the ownership system, and we'll get into exactly what that is. But basically, this term is well, this radical wager that Rust presents is really kind of a fundamental shift in how programming languages might want to handle memory management, as we'll see in a second. But so basically, Rust as a low-level language, the philosophy behind it, and what the developers and designers really wanted to emphasize above anything else was safety. And at the same time, though, they wanted to keep the language at least as fast as C++, which seems like a tall order, right? Because C and C++ generally are not considered completely safe, right? Because again, you get like a lot of undefined behavior in C and C++. There's a lot of wrong ways to do things in those and other languages, and Rust from the get-go was like, we want to eliminate any possibility of any of that sort of behavior, but at the same time, we don't want to lose performance when being compared to C++, which again, basically rules out garbage collection, right? Because C++ doesn't do garbage collection. So from there, the ownership system really has to do with memory management. So let's talk a little bit about ways that languages ensure that resources get cleaned up, right? So again, first with C and C++ and languages like that, those languages put the onus on the programmer to clean up after themselves. And they assume you're going to do it correctly and that you're always going to do it correctly in every situation. But if you don't, then we get like undefined behavior and bugs in your code and security holes and things like that. Because people are not perfect, and developers certainly will forget to do things or do things incorrectly from time to time. And those languages really don't really help you in any way on that front. They just assume that the programmer is perfect and benevolent, and that everything is going to get done exactly the way as it's supposed to. The other kind of major paradigm is, of course, implicit garbage collection, right? So a lot of languages like JavaScript, I believe Java, Python, they just decided we're going to build in a program into the runtime of these languages, and the sole purpose of this program is going to be, when it's executing, it's going to clean up resources. So the onus is not on the programmer, it's on the language to actually do all of the work. And this works well for a lot of modern languages today, but in Rust's case, since the developers and designers decided we still want Rust to be at least as fast as C++, this was a no-op. So they had to really kind of think about, what's another way we can ensure that resources get cleaned up without allowing the developer to make mistakes, but at the same time not having the program have to put in a lot of work or put in any work to clean up the resources implicitly. And again, they came up with this ownership system, and basically the gist of it is that they basically made it such that the compiler enforced certain rules about how things like variables and memory and ownership, which we still haven't talked about, but we're going to get into what that is in a second, how those particular concepts are enforced and can be enforced in such a way that the compiler can basically catch any misuse of memory. And that really involved a lot of kind of fundamental shifts in how the language kind of deals with memory. But basically, they wanted to make it really simple, to make the rules really simple for ownership, and again straightforward, such that the compiler can actually do all the work of checking the programmer's work when the programmer tries to compile their code. So that if the code actually successfully compiles, then you can be sure that it is safe, in the sense that there's not going to be any undefined behavior. You're not going to be mishandling any sort of memory. But at the same time, garbage collection is being taken care of in a non-resource intensive fashion. So we're going to get into a bunch of examples and stuff, but that's basically the gist of it. And this was the slide where I was like going to introduce the word ownership, but I think I jumped the gun, so maybe the slide is not necessary, but whatever. Okay, so these are the rules of the ownership system that I'm going to present up front. And you're going to look at these and you're going to be like, well, these don't seem like much of a paradigm shift at all. These don't seem like much. But as we'll kind of see with these rules, it's again, because the rules themselves are very simple. I think it's at first it's probably seems really subtle how they actually affect the rest of the language, but and really you kind of need to experience it for yourself. But really, I think if you actually start, for example, writing some Rust code, I think you'll start to realize that most people are very much used to certain to being able to do certain things in the languages that they're comfortable with, and Rust actually forces you to unlearn a lot of that stuff in the name of its ownership system. But I guess most notably, one is not very special. I think two maybe is well, we can read that be there's only one owner of a value at any point in time. Again, we don't know what that means yet, but I think that's the one that has maybe the most implications. And then three is actually alluding to how Rust actually performs the freeing of memory and stuff like that, the actual explicit garbage collection. But what's interesting is that in a sense, Rust does have implicit garbage collection. It's just that it's so kind of simple to perform that the computer or the language itself doesn't need to do any sort of computation, right? It's just like it just follows these rules that are really simple to compute, and if those rules are fulfilled, memory gets freed. So basically, the language makes it dead simple to know when memory needs to be freed. Okay, so let's look at some C code. This looks a bit garish now when I do it full screen, which I didn't realize would be the case when I was typing it up. But anyways, so let's say we have this struct owner in C that has nothing on it but an array of strings representing things that this owner might own, for example. So like lower down, we see like a bicycle and a laptop, right? So we'll initialize some memory for the owner struct, and then we'll initialize some memory for the owned things array. So we'll give it space for 10 strings, 10 string pointers. And then let's say we start filling up the owned things array with some strings. So this owner owns a bicycle, a laptop, maybe some other things. And then what C allows us to do, and really what most languages allow us to do, is they'll allow us to basically take another reference to to an owned thing, right? So we could say char star bicycle equals the bicycle that the owner owns. So we can get another pointer from somewhere else in the program that will reference that same thing, right? So if we want to think about if we want to think of it this way, before the last two lines at the bottom, pretty much only one thing referenced the bicycle and the laptop, right? And that was the owner. But it's really easy in a lot of languages to just be like, oh, I can take a reference to something that's owned by something else really easily. And that's totally fine in most languages, right? And so then what's to stop us from just say doing like just having some function like this that will end up freeing whatever freeing the value that it gets passed in. So for example, if we have this function, it ends up calling free the thing that it received as an input, and just calling that with the reference with the second references that we had from the last slide. Right? Because basically my point being here is that the owner struct really doesn't own the things that are in it, right? So like the bicycle and the laptop that, again, we kind of initialized it with, it doesn't have complete say over when that memory gets freed, because there's nothing stopping us from freeing that memory from some other part of the program. Right? And so that then opens up the possibility for those references to be null when, for example, that owner wants to use it again, which opens up the possibility for things like undefined behavior and other such security holes and things like that. But I guess the gist of what I'm trying to say is that most languages, again, they just allow you to kind of take references to anything, to any objects or values in memory, and they don't stop you from throwing out as many of these references as you want, right? So it becomes really, these ownership dependency trees that maybe get really complex and mangled, which is why a lot of languages have to resort to a program like a garbage collector that can do the work of manually inspecting each of these objects and values in memory and just checking to see, I'm able to free this now when there are no references to this thing. But again, because the languages allow the programmer to put references wherever they want, that can get computationally intensive. More specifically, it's, as we saw yesterday from the Wasson presentation, garbage collectors can make performance very unpredictable. So this is essentially what Rust's ownership system prevents, is these kinds of crazy mangled ownership dependencies. So let's look at some Rust code then. So here we have a main function. We're declaring this variable s1, and we are initializing it to a string. Specifically, with this string from method, we're allocating a string on the heap instead of on the stack. So it's not a static string. We then might be able to do some stuff with s1. And then at the end of the main function scope, S1 gets what's called dropped. So Rust's terminology for freeing up memory or deallocating memory is dropping it. And that literally just happens at the end of the scope. Doesn't matter that the memory is on the heap. If we've reached the end of the scope, we're dropping that memory. So it actually turns out in Rust code, you don't need to explicitly call like a free or like C++'s delete or anything like that. You don't need to actually manually do that. You can if you want, but it's not necessary. Right, so again, we're just like end of scope, we're dropping that memory. And so outside of the scope, there's no way to reference S1 outside of it. At least, well, yes, there are ways, but you'd have to, anyways. There are ways, but just point being is that at the end of the scope, that memory just gets dropped. And that's really easy for the compiler to enforce when it's just reading this code. So let's say now we wanted to do something like this. So we just go and initialize a variable s2, set that equal to s1, and let's say we decide to go and print s1. If we were in any other programming language, we would expect this to work just fine. But it turns out this is not something the compiler will let you do. And so he's looking at the error message here. At the top, it says use of moved value s1. So what the heck does that mean? So basically, when we did that assignment, let s2 equals s1, instead of s2 just being another reference that points to the hello string, like in this representation, where again, this is what most languages would do, where S2 and S1 are both pointing to the hello string. This is not what actually happens in Rust. What actually happens is S2 takes ownership of the string hello, meaning S2 is now the only variable that owns the hello string. And S1, which used to be the owner before we did that assignment, is now invalid, and we're not allowed to use it. And so this is what I was kind of talking about when I was saying earlier that in Rust, every value, every object in memory at any one time only has one owner. And again, right now with these examples, maybe we don't see any sorts of implications with this. But I guess, and we're not really going to get into a lot of those implications because that would involve a lot more, much more kind of complex examples, I guess, to kind of really understand the implications. And really, like, understanding these implications and what they mean for the language really is kind of like the central, I would say, hurdle when it comes to learning the language. And honestly, I feel like I don't even have a full, firm kind of grasp of all of it at this point myself. Okay. So this works where, same thing as before, we let S2 equals S1, we are allowed to print S2. So that's not going to give us any errors because now S2 owns the string, the hello string.
Hey, Sean, can I ask a question?
Yeah, what's up?
When S2 is assigned to S1, now that, in this one here, does S1 get dropped at that,
Yeah, so that's a good question. I probably should have checked that, but I'm pretty sure S1 does not get dropped. It doesn't get dropped as well into the end of the scope. So it still like hangs out as, just like an invalidated variable in the scope. And I guess, to be honest, I'm not sure if you could like do something. I think what you could probably do is, like, if you wanted to have it take ownership of some other value by doing another assignment, I think that would work. But right. I would have to check that in a REPL or something like that.
Thanks.
I'm pretty sure S1. I mean, S1 definitely is getting dropped at the end of the scope, but I think until then it's not getting dropped. It's just hanging out, being invalid. Okay, and then we can do something like this, where again we initialize S1 and S2. We explicitly call a clone method on S1 and set that to S2. So now once we've done that, we can definitely print both S1 and S2. And the memory representation, as we can guess, in that case is now S1 is pointing to its own instance of the hello string, and S2 is pointing to its own separate instance of the hello string. And there's no issues here with the ownership system because now we have two separate instances in memory, and both of them need an owner. So let's move on to another example. So here, the ownership, the moving of ownership can also happens between functions. So for example, again, with now it's just S, the hello string, we can call it with this function that it's just called takes ownership, and all it does is it prints whatever it received. But the gist of it here is that because this takes ownership function receives the string hello from the variable S, it now becomes the owner of the string S when we're in the scope of the takes ownership function. So takes ownership is able to go and print the value from the string, and in the main function, after takes the ownership of the string, it is not able to actually use that value anymore. It doesn't have access to that value anymore. It's a slightly different story with when we just say let x equals 5, because in the case of integer values and pretty much all the numerical values and booleans. So any static values in memory. Rust just instead of having them be owned by any one value, by any one variable at a time, it just allows those to be copied. So what actually goes on here between when we compare takes ownership with the makes copy function, because the makes copy function is just receiving some 32-bit integer, instead of having that integer value be moved when makes copies scope, when we enter the makes copy scope, it literally just copies that value. So we'd still be able to use x in the main function after we call makes copy, and makes copy has its own copy of the integer. But again, that only works for numerical types, booleans, and I think I'm forgetting some other things, but any of those kind of like static types that don't require any sort of dynamic memory, which is not strings. So strings are not inherently copyable, or I should say not implicitly copyable, but as we saw earlier, you can explicitly call a clone method in order to perform a copy. Okay, so if we just had the concept of moving things back and forth, I think that would be, well, that would make the Rust language certainly not flexible whatsoever. So of course, there is the concept of references, and there's the concept of references. So instead, what we can do, in contrast to the earlier examples, is we can pass a reference to the S string, which then means in this case that the S variable still owns the hello string. So the analogy here is, when you own something, like something physical, like a book, you as the owner are freely able to lend that book out to someone else with kind of the stipulation that they're going to give it back. So this is kind of that same idea, except with here, you are able to lend out as many references to the hello string as you would like, so long as those references are used for reading only. Okay, so this example is fine. We take a reference to the S string, that gets passed into this borrow function, and again, borrow just prints. It doesn't actually do anything. Well, it prints that out, and then after this whole ordeal, the S variable still owns the string. And again, this is fine because when borrow took in that reference to S, it didn't seek to mutate or change whatever it was referencing, right? Which is what we might look at here now. So if we were to instead try to do something like this, where the borrow function takes a reference to some string, for example, and then tries to do something like push some additional characters onto the end of that string, which would be considered mutation, that's a no-op, because we borrowed S, the string S, immutably. With the normal ampersand syntax, that signifies that we are taking a reference to something and we only wish to read the value. We are not seeking to actually mutate it. So it tells us here you cannot borrow an immutable borrowed content as mutable. So but basically at the same time, if we want to borrow it as mutable, we can certainly do that. So we would just have to abbreviate this mute keyword in front of S, and then also state that the reference is going to be mutable. So now we can do the borrow and change that we were seeking to do earlier. I think the syntax isn't entirely correct. I think in the signature of borrow and change, it needs to be and mute capital string. But anyway. So now this would work. Another example that would not work is that we are not allowed to have multiple mutable references to something at one point in time, right? So R1 is if we just had let R1 equals and mut S, that would be fine, because at that point we only have one outstanding mutable reference to the S string. But then let R2, that second line that comes along, also tries to declare a mutable reference to S. And then when we try to compile this code, it's going to tell us that we cannot do that. You can only have one mutable reference to some owned value at any one point in time. And also, this is also a no-op, where we also cannot have any other references to something as long as a mutable reference to it exists. So as far as the ordering of the code here is concerned, R1 and R2 are fine if R3 was not initialized, right? So we can have multiple immutable references to S, as many as we'd like, but until all of those references are no longer valid, and there are no other, as long as there are no other references to S, that's the only time we can then take a mutable reference to S. Because the idea then there is that if there's a mutable reference outstanding for some object or some value in memory, there's always the possibility that that value can be changed because there's a mutable reference outstanding, and because other values might have references, even though they're immutable, to that value, that opens up the possibility for data races. So Rust inherently, as a result of this ownership system and the way it enforces the use of references, it eliminates the possibility of data races just by virtue of the syntax, essentially. And again, a data race is where you have the possibility of data not being in sync because, for example, there is something that's mutating the data, and then other things that are trying to read that data at the same time, read or access that data at the same time. And so it's very easy for data to get out of sync if, again, for example, you have the possibility of being able to mutate or change some values and other things trying to reference that that value that might be being changed. So just by virtue of the fact that the compiler doesn't allow you to even do this, inherently there is really no way to have a situation where a data race might arise. But that being said, race conditions are a totally different story. Okay, so again, compiler doesn't let you do that. And so really, I think at the end of the day, what Rust tries to do in terms of how it structures things in memory, it really tries to be a lot more kind of ordered with it, right? Again, because of the fact that no one value can have more than one owner at any point in time, and things like that, that really kind of fundamentally changed how you interact with values and objects in memory. And so I think at the end of the day, in a sense, Rust is less powerful than languages like C, C++, Python, JavaScript, whatever, in the sense that it doesn't just let you take references willy-nilly to any value in memory. So in that sense, pointers are a lot less kind of flexible. But the trade-off for that is that the way then that ownership dependencies are represented in memory is a lot more straightforward. And so it becomes a lot easier to go and allow the compiler to be able to really easily figure out, when to actually drop something and free some spot in memory up And that just happens when its owner goes out of scope, because again, there's only one owner. So once that owner goes out of scope, we can just drop that memory. Doesn't matter. We don't have to do any sort of reference counting, because again, there's only one owner and things like that. So we don't need an implicit garbage collection system. And so that's kind of, well, we'll get into pros and cons of the ownership system right now. And so again, it makes it so that Rust is completely safe. You're not going to get any sort of weird undefined behavior, assuming you use it in the ways that are prescribed and idiomatic to the language. What's also really smart about how the developers designed Rust is that even though there is this prescribed and idiomatic way of doing it, with the ownership system and all that stuff we've just been talking about, it does also provide backdoors and other options built into the language for developers to opt into if they want to. So there are ways to circumvent a lot of these safety practices. But again, by nature of the fact that you have to opt in, at that point, it's like, all right, Rust will say, I'm assuming you know what you are doing because you opted into this feature or into this option. So now if anything goes wrong, the onus really is on you this time. So I think it's really smart with how it kind of balances that. So again, people who maybe have more of an idea of what they're doing can open up more flexibility in the language. But that being said, I think even if you just use it completely as it's prescribed, Rust is actually not that bad in terms of flexibility. Again, we've already said this, but the ownership system guarantees that your code will be free of data races, even when you're using Rust in a concurrent manner. Well, I should say, especially when you're using Rust in a concurrent manner, because that's mostly where data races become an issue. But again, race conditions are a different story, because a lot of those have to do with, with race conditions. That has more to do with like timing of like when things get accessed in concurrent code, and oftentimes it has to do with the logic of how you wrote that concurrent code. And so race conditions, I don't really think there's any way for a language to stop you from making race conditions in a reasonable fashion. But anyway. And again, I've gone ahead of myself and we've already talked about this. I guess because I'm just that eager. But again, there are options to the programmer to opt out of its safety guarantees, and with the understanding that if things go wrong at that point, it's on you, the programmer. Okay, as far as some cons, and of course there are cons, but really one thing that I personally have found difficult learning the language is that, again, because of this fundamental shift in how values and memory are handled and things like that, Rust's idioms really are very different. And it doesn't, like, well, I'm not going to say, knowing other languages doesn't help, because it does help. But at the same time, a lot of idioms that maybe you are used to from other languages really do not necessarily translate over to Rust, because, again, of this fundamental kind of shift that is really baked into the language. And really, I think one of the main hurdles, at least for me, is finding lots of good examples of like idiomatic Rust code to kind of learn from. And another thing being that I think Rust definitely requires a certain level of persistence and perseverance when you're first learning it, because because the compiler stops you from doing a lot of things that, again, maybe you're used to being able to do coming from another language, right? But it's going to take you a lot of time before you really internalize the fact that, oh, I can't just take, I can't just do a variable binding and just pass references like that around as much as I want, like what I'm used to doing from other languages, right? You're going to try to do that in Rust, and the compiler is going to tell you, no, you can't do that. And you're going to be like, why? Because you haven't, it's not, you haven't really assimilated that fact yet. But anyways, let's coming back to that radical wager that we talked about in the title screen. And really this whole ownership system is Rust's radical wager, that this system and the way that Rust implements it and allows the developers to leverage it and take advantage of it really is, that this is worth it, right? That fundamentally kind of changing how you think about how values in memory are owned and working with them that way, that really brings a lot of safety benefits to the table when it comes to memory management and concurrency bugs. And in C and C++, for example, writing concurrent code is really freaking hard because there's so much possibility for doing incorrect things and data and for example, if you forget to if you let some data races slip in and things like that. And I don't remember, I think this was yesterday when we were talking about writing operating systems. I think this was at the end of the session yesterday when we were talking about, writing like an operating system in Go or writing an operating system in Rust, which is a thing that is an open source project that's currently being worked on, by the way. I think Beej mentioned that, yes, Linux is written in C and that it had to be kind of really painstakingly and manually inspected to ensure that all of the C code was adhering to best practices and wasn't letting in the possibility of security holes and leaks and stuff like that. And really, if the Linux kernel had been written in Rust from the get-go, that really would not have been a thing that they would have had to deal with. Like, just by the fact that the code, when the developers were writing it, that the code compiled is a huge kind of boon in the sense that that code is safe. And like, frankly speaking, I think when I go back to writing C code now from Rust code, it kind of feels like I'm like walking on matchsticks or whatever the term is, or like trying to assemble a house of cards now when I used to be like using some much more robust kind of construction tools. And I think at the end of the day, I think what I really identify with in terms of the way Rust kind of structures all this is just the philosophy of short-term gains versus long-term growth, right? So again, when you're first learning Rust, the learning part is much more of an ordeal than if you tried learning some other language. Because in other languages, they don't try to get in your way from the get-go. They allow you to kind of do things however you would like. And if you make mistakes doing things however you would like, that's on you, right? So in the case of Rust, really the compiler kind of babies you when you are first learning. Tells you what you can't do, kind of like gatekeeps off certain like features until you feel like you can opt into them because you are comfortable enough or you feel like you know enough. And so, yeah, it really is like a gatekeeper in that sense. A gatekeeper to like those kind of short-term gains that you might get from learning a language. But that's not to say that, you won't eventually get past that gatekeeper once you kind of learn to and figure out how to do things in idiomatic Rust fashion. It's just rather different, and it kind of does force you to be cognizant of or unlearn a lot of things that you are used to from other languages. And frankly, I think these really are things that the things that Rust wants you to learn are also considered best practices in C and C++ as well. It's just that in C and C++, the compiler doesn't enforce those on you, right? And that really is kind of the key main difference in that, humans are fallible. And so it's really nice when you have the machine, which in a sense is a lot less fallible, telling you when you're doing something wrong so that you can kind of learn and grow from that instead of the machine just not letting you do whatever you want. And so your learning can kind of segue all over the place in a sense. And I guess for me personally, I certainly adhere to the philosophy where I believe that long-term growth is almost always more worth it than short-term gains. But that's just me. And then some other pros of the language, in case you need more convincing, I guess, is that I feel like Rust's error messages and compiler messages are hands down the most readable and unambiguous that I've ever seen. So the ones that we've been looking at so far throughout the presentation, those are actual compiler error messages from the Rust compiler. That's how they're structured, and that's how it tells you you're doing something wrong. It tells you not only the line, it tells you exactly, which part of the line, which column it starts on. And I think other languages do that as well, but like the fact that Rust will like print that line out again for you and point arrows at it exactly, saying exactly this is where your problem arose. I think it's just like an extra layer of polish on top of the compiler error messages that I find pretty welcome, at least. And honestly, I've had this thought before that because I feel like when a lot of students first join Lambda, and students are just kind of starting to learn programming in general, error messages are really scary. When you do something wrong in your code and your interpreter or your REPL or your compiler or whatever throws up an error message, I think for a significant number of people, the first instinct is just to run from the error message and be like, oh my gosh, I got an error. I'm not going to bother reading this. I'm just going to go and paste this in the help channel and see what other people say. I was certainly guilty of that when I first started learning programming. I would encounter an error message and be like, nope, that's scary. I'm not going to read that. and just go and immediately seek help before even trying to diagnose my own problem. And this idea that I've had is that, I think maybe in like the pre-course, there needs to be just like some section where literally all we have the students do is we just give them an image of an error message and have them answer questions about what is going on in that error message. If nothing more than as kind of like a way to get people to realize that error messages are not actually scary things. And I honestly was thinking that maybe we should just use error messages from the Rust compiler for this, because I think those are kind of the most friendly. Certainly if we went with like C compiler error messages, I think maybe that could be a little intimidating. But anyways, there's lots of good documentation. There's lots of good books, a lot of good learning resources out there. What's also been really cool is a few universities have also been experimenting with things like teaching a class in Rust or teaching like a university operating systems class in Rust. They're kind of few and far between, but I really like seeing that sort of experimentation and not just being like, operating systems have historically been taught in C. We're just going to keep going with C. So I think that's really cool. And I'm hoping that Rust will kind of start to be a very viable option for moving away from C for a lot of like code bases and things like that. It's a modern language, so it's not like C in the sense that you have to do everything manually. So all those modern language bells and whistles, all those juicy array methods that you're used to, it has a lot of functional programming paradigms folded in, so you can get pretty functional with it, and things like that. So it's not, you won't feel like you have to keep doing everything super manually like you do in C. And it has a really awesome and easy to use package management system. I honestly think it's better than npm, but that's probably coming from me, who is a fanboy. So you can take that with however many grains of salt you would like. Okay, and then a list of resources for learning Rust for any of you who might be interested. The Rust programming language book is pretty much, this is the main book that's written by the documentation authors of the language. So what's really cool is, this is, well, there are engineers on the Rust team who literally just focus on Rust documentation, and like they wrote the definitive book for the language, freely available on the Rust docs site, in case you're interested in reading that. The second one is the one I really like. I'm not actually sure who the author is. I could probably look it up, but I really haven't. Learning Rust with entirely too many linked lists. I really like the idea. And literally he goes through, talks about Rust concepts, and implements increasingly more complicated linked lists for the more chapters you go in. So I think it's a great way to, certainly kind of a funny way to structure a language tutorial, and it's pretty great in my opinion. Programming Rust by Blandy and Orendorff. This book came highly recommended as well. Unfortunately, you do have to buy it, but it's certainly, it's really nice in the sense that, well, I think it's personally helped my learning, because I have read the Rust programming language, I think, a couple of times now at this point. And it really helped when I kind of got a different perspective on a lot of the concepts and topics in Rust. And the Programming Rust book certainly does that. It explains things in a very different fashion, which I really appreciate. And I think, again, when you're learning, different perspectives certainly will speak to different people. And I think maybe the Programming Rust book maybe spoke to me a little bit better than the Rust programming language book. And then, just for fun, one at the end, there is a rather large and sizable tutorial called Writing an OS in Rust, which is pretty much, as you can imagine, what that is. But it's pretty great as well. So again, there's a lot of resources out there. I think what I would mostly wish for more is just like a more readily available resource for like idiomatic Rust snippets of code. I think certainly you could comb through GitHub to find it, but I would just wish there was something that was more available / easily searchable and things like that. But if you're looking for like comprehensive tutorials / books and things like that, there's quite a number of those out there. But yeah, that is it for this presentation. Now I can see what people have been saying in Slack. Sounds like C is a socialist. Yeah, in a way, right? And but it's not just C, it's like most languages. Like, yeah, they don't have this clear concept of ownership and who is owning some value in memory at any one point in time. Yeah, interest free. Yeah, it gets really hairy then when you're even like trying to write like a doubly linked list, because every node, for example, in a doubly linked list has multiple references referring to it. Um, there there are ways to get around it. I think a lot of it involves a lot of those constructs that we were talking about earlier that you have to opt into to kind of get out of the prescribed Rust way of doing it, uh, which is interesting. Like I know that for I actually wonder if I feel like for if you're implementing like just like a binary tree, whether it's actually more idiomatic in Rust to just implement it as an array, like we saw when we did heaps. But like things like that, again, you know, pretty radical ways in thinking about how you might implement certain data structures and things like that. Um, if you're interested in some code for a BST, I do have a link. Again, that's a binary tree example, if you're interested in seeing what that looks like in Rust. Generate the longest error message in C++. No idea if the Rust codes are any good. I've done fundamental languages. Oh yeah, that is a thing. No, I do not know who that is. Oh, that's a good Mike McDonald. I'm assuming he knows a thing or two about Go. Oh yeah, you're right. That's funny. All right. So that's it for my presentation. I don't know if people had any more questions or anything like that. Nice. So I don't know if this goes without saying, but you know, this is just stuff I find interesting. If you don't find it interesting, feel free to not give a crap. I'm not going to be offended. It was fun for me just even putting this slide deck together. So I guess thanks for indulging me on that front. All right, cool. I guess if there's no further questions, I'll let you guys get back to Game of Life fun. And then tomorrow, no meeting in the morning, but we will be doing demos at 2 p.m. PST. All right. I will see you guys later then. Have a good one.